Many industrial processes must heat or cool fluids to produce products. Heating and cooling are often accomplished by transferring heat between fluids. Heat transfer between fluids occurs in heat exchangers. There are many types of heat exchangers, but one of the most common types is a shell and tube heat exchanger. Shell and tube heat exchangers can be used for a variety of processes, and operating procedures may vary with each heat exchanger. What you'll see here is intended to be a guide to the steps that often have to be taken in the startup of a shell and tube heat exchanger after it has been shut down for maintenance. But remember, always follow your facility's operating procedures when you're starting up any heat exchanger. The unit we'll be using is part of a mixing process and is used to cool the process liquid. The heat exchanger has cooling water inlet and outlet lines, process liquid inlet and outlet lines, a series of isolation valves, a vent valve, and drain valves. Before starting up the heat exchanger, the operator inspects the unit to see if it's ready. He checks the valves to make sure that all of the isolation, vent, and drain valves are shut. After he completes the initial inspection, he establishes the cooling water supply to the unit. He does this by calling the control room operator and having him open the shell side vent. Then he partially opens the shell side water inlet valve to slowly fill the shell side. Then he calls the control room to have someone there start the cooling water pump. When the cooling water pump is started, cooling water will fill the shell side of the heat exchanger. Any air that is trapped on the shell side escapes through the open vent valve. As the shell side of the heat exchanger fills, the operator listens for air escaping. When the shell side is completely filled, he calls the control room and has them shut the vent valve. Then the operator opens the shell side inlet valve the rest of the way. At that point, he informs the control room that the shell side is lined up and that they can establish the proper flow rate through the shell. On the heat exchanger shown in this example, there is no isolation valve on the outlet of the shell side. Some shell and tube heat exchangers have an isolation valve on this outlet. With those heat exchangers, the isolation valve must be opened to complete the flow path through the unit. The next step is to line up the tube side of the heat exchanger. First, the operator opens the tube side vent valve. Then he partially opens the tube side inlet valve to allow the tube side to fill with process liquid and to remove any air or other gases that might be trapped on the tube side of the unit. When the tube side is filled, the operator closes the vent valve and opens the inlet valve the rest of the way. Then he opens the outlet valve. At this point, the startup is complete and the heat exchanger is in operation. After the operator reports to the control room that the unit is in operation, the control room establishes flow through the unit. Shell and tube heat exchangers are commonly used in a variety of processes, and each may have a different operating procedure. But remember, always follow your facility's operating procedures when shutting down any heat exchanger. During shutdown, the side of the heat exchanger with the hotter fluid is usually shut down first. This helps to prevent the heat exchanger from being overheated and damaged. Let's watch an operator as he takes a heat exchanger out of service. In this example, the heat exchanger, which cools a product from a reactor, is being shut down for maintenance. The tube side fluid is the hotter fluid. To shut down the heat exchanger, the operator closes the tube side inlet valve first, and then the tube side outlet valve. When the tube side has cooled, the operator opens the tube side drain and vent valves. This allows air to enter the tube side and drains the process fluid. The operator then shuts the shell side inlet valve. On the heat exchanger shown in this example, the shell side has no isolation valve on its outlet. Some shell and tube heat exchangers have an isolation valve on this outlet. With those heat exchangers, the isolation valve must be shut to completely isolate the heat exchanger. After the isolation valve is shut, the operator opens the cooling water drain and vent valves. Once all of the fluid is drained from the heat exchanger, the operator closes the vent and drain valves to complete the shutdown. Now, if the heat exchanger that's being shut down handles flammable liquids, it may have to be purged to reduce the possibility of a fire or an explosion caused by flammable vapors. Purging means forcing the process fluids out of the heat exchanger by a substance that won't react with the process fluid. Very often, steam or nitrogen is used. When a heat exchanger is in operation, operators must routinely check the unit to ensure that it's operating properly. This may include checking temperature and pressure instruments to make sure that their readings are within normal operating ranges, as well as checking the condition of the heat exchanger itself. By checking a heat exchanger's temperature instruments, an operator can tell how the temperatures of the fluids change as they pass through the unit. These values can also be used to determine the difference in temperature, or delta T, for each fluid. The delta T can be used to see if the unit is operating properly. For example, if the delta T across the tube side of a heat exchanger is supposed to be 10 degrees, but it is only 5 degrees, it could be an indication that the tubes in the unit are becoming fouled, or that one or both of the flow rates are not correct for proper operation. In any event, the cause of the problem should be investigated, and supervisory personnel should be informed. Another way that temperatures can be checked is on a temperature recorder. The recorder plots temperature values on a chart, which allows an operator to see if a trend is developing. Additional information about a heat exchanger can be obtained by checking the unit's pressure instruments. By reading the pressure instruments, an operator can often detect problems with flow through the unit. Anytime there's flow through a heat exchanger, there will be a specific drop in pressure across the unit. This pressure drop is often referred to as differential pressure, or delta P. Any change in differential pressure could be an indication of a problem. As the tubes become blocked or fouled, the differential pressure will increase above the normal value. Once again, the cause of the problem should be investigated and supervisory personnel should be informed. On many units, temperature and flow are controlled by automatic systems. These systems may provide indications locally and in a control room. The indications in the control room can be compared to the indications on instruments located at the heat exchanger to verify that the heat exchanger is operating properly. If a problem is detected, it could be the result of the control valves not operating properly, or valves being out of position. Or it could be an indication that other equipment associated with the heat exchanger is not operating properly. For example, a low inlet pressure could indicate a problem with the pump that supplies the heat exchanger. Besides checking instrument readings, an operator should also check for leaks and for damaged or missing insulation. Problems such as these could affect the operation of the heat exchanger and pose hazards to personnel working in the area. In this topic, we looked at some basic procedures for the startup and shutdown of a typical shell and tube heat exchanger. We also looked at some operator responsibilities associated with operating a shell and tube heat exchanger. Now let's try a few practice questions. When the cooling water pump is started, cooling water will fill the shell side of the heat exchanger. Any air that is trapped on the shell side escapes through the open vent valve. As the shell side of the heat exchanger fills, the operator listens for air escaping. When the shell side is completely filled, he calls the control room and has them shut the vent valve. Then the operator opens the shell side inlet valve the rest of the way. At that point, he informs the control room that the shell side is lined up and that they can establish the proper flow rate through the shell. To shut down the heat exchanger, the operator closes the tube side inlet valve first, and then the tube side outlet valve. When the tube side has cooled, the operator opens the tube side drain and vent valves. This allows air to enter the tube side and drains the process fluid. As the tubes become blocked or fouled, the differential pressure will increase above the normal value. Once again, the cause of the problem should be investigated and supervisory personnel should be informed. Fouling is a term that's often used to describe the buildup of deposits on the internal surfaces of the heat exchanger. When fouling occurs, the result is an additional layer of material that heat must pass through. This additional layer reduces the ability of the unit to transfer heat. Also, if the buildup becomes excessive, the flow of fluids through the unit may be restricted. Fouling can be caused by many things. One common cause is impurities in the fluids passing through the heat exchanger. For example, in a process that uses water, impurities such as calcium can come out of the water and form an additional layer of material. Another source of fouling is small plants and animals that enter the heat exchanger. Many forms of algae and bacteria can live and grow inside the unit and form a layer of slime on the internal surfaces of the heat exchanger. Gases dissolved in the fluids that flow through a heat exchanger can also cause fouling. For example, some gases react with the metal inside a unit to cause a type of corrosion. The corrosion forms a layer that acts as an insulator, just like impurities or algae. Different techniques can be used to minimize fouling. For example, filters and screens can be used to remove particles from the fluids before they enter the heat exchanger. Fouling can sometimes be minimized by adding chemicals to the fluids passing through a heat exchanger. For example, chemicals such as chlorine are often added to cooling water to reduce the amount of algae or other organisms inside a unit. In some situations, fouling can become bad enough to restrict the fluid flow. This problem may show up on the heat exchanger's instruments as an increase in the pressure drop or as a gradual decrease in the flow through the affected side of the unit. Fouling may also affect the temperature of both fluids passing through the heat exchanger. When fluid flow is restricted, the heat exchanger must be cleaned. One way that heat exchangers can be cleaned is by using chemicals. When this is done, a chemical solution is passed through the heat exchanger to dissolve the fouling on the walls of the tubes. Fouling on tube walls can also be removed by scraping or by spraying with high-pressure water or steam. However, these methods require the heat exchanger to be shut down and taken apart. In some heat exchangers, cleaning can be accomplished using a technique called backwashing. Backwashing is the reversing of flow through the heat exchanger. This technique is effective in temporarily dislodging materials from the ends of the tubes and the tube sheets. Tube leakage is a problem that can seriously affect the operation of a heat exchanger. It's usually caused by the failure of a tube as a result of overheating, erosion, or corrosion. Erosion is the wearing away of tube metal caused by the flow of fluids or by solid impurities in the fluids. Some fluids that pass through a heat exchanger may contain abrasive particles. As these fluids flow through the heat exchanger, the particles come into contact with the tube metal and erode the tubes. Eventually, the tube wears away in a spot and a leak forms. Corrosion chemically deteriorates tube metal to create a leak. Corrosion is caused by a chemical reaction between the metal in the heat exchanger and either the fluid passing through the unit or impurities in the fluid. The corrosion weakens the metal until a leak forms. The biggest problem that can result from leaks in a heat exchanger is the mixing of one fluid with the other fluid. For instance, if cooling water mixes with oil in a lube oil cooler, the water could damage the equipment that the oil lubricates. To prevent this type of damage from occurring, leaks must be detected. One way to check for tube leaks is to take and analyze a sample of the lower pressure fluid. When a leak occurs, the high pressure fluid leaks into the low pressure fluid. In some cases, you may be able to tell there's a leak by just looking at the sample. In other cases, a lab test may be required. To prevent leaks in some applications, the process fluids pass through filters or strainers to remove impurities that can erode the tube metal. Also, chemicals may be added to the fluids to control corrosion. Another method of controlling corrosion involves using a device called a sacrificial anode. When a sacrificial anode is used, impurities in water tend to react more readily with the anode than with the metal of the heat exchanger. So the sacrificial anode corrodes while the heat exchanger is less affected. Heat exchangers that are used with water often have sacrificial anodes made up of zinc plates mounted inside. When a leak does occur, some type of corrective action must be taken. If only a few tubes in a heat exchanger have leaks, it may be possible to plug the affected tubes. This prevents the tube side fluid from passing through those tubes and effectively eliminates the leak. However, plugging tubes reduces a heat exchanger's heat transfer capacity. If a lot of tubes are leaking, the unit will have to be shut down and the affected tubes will have to be replaced. When air, non-condensable gases or other vapors are trapped inside a heat exchanger, they can prevent the unit from operating efficiently. This is because the air or gas can either blanket the tubes or block the tubes off and prevent fluid from flowing through them. The effect is the same as the effect created by fouling. Less heat can be transferred across the tubes. Gas trapped on the tube side of a heat exchanger can block off tubes and prevent fluid from passing through them. Gas trapped on the shell side can displace the shell side fluid at the top of the heat exchanger. This can reduce the amount of tube surface area that is exposed to the shell side fluid, and thus reduce the amount of heat that can be transferred. There are many ways that air or other gases can get trapped inside a heat exchanger. For example, this can happen during the startup of the unit. During startup, the heat exchanger should be vented to remove unwanted gases. If the venting is not complete, gases will remain inside the unit. Another source of gases is the process itself. In some situations, the process can produce vapor bubbles. As the process fluid passes through the heat exchanger, the vapor collects inside the unit. When maintenance is performed on process equipment, air may be trapped in the piping or shell as the equipment is put back together. When the equipment is restarted, the air can make its way to the heat exchanger and become trapped inside. No matter how air or other gases get trapped inside a heat exchanger, they can cause it to become air-bound or vapor-bound. There are several symptoms to indicate this. For example, when trapped gas blocks flow to some of the tubes, the outlet temperatures of the two fluids may change. This is because the gas is restricting flow into the tubes, and the restricted flow causes less heat transfer surface area to be available. The decrease in heat transfer surface area will cause the outlet temperature of the process fluid to increase, since less heat will be removed from the fluid. There are also situations where the pressure inside a heat exchanger may be affected. For example, this can occur in heat exchangers that are used to condense process vapors. In this situation, non-condensable gases partially fill the unit, reducing the amount of heat transfer area that the process vapor can come in contact with. In turn, this reduces the amount of vapor that can be condensed. The flow of vapor will start to decrease, and the pressure inside the unit will start to increase. Regardless of how gases get into the heat exchanger, the unit must be vented to allow them to escape. Repeated venting may be necessary to ensure that the heat exchanger remains free of air and other undesirable gases. However, excessive venting can cause its own problems. For example, each venting may allow a small amount of the process fluid to be lost from the process. This reduces the efficiency of the process. Venting may be only a temporary fix. If the source of the gas is the process, there may be a problem with the process or with one of the components in the process. In this topic, we looked at some of the basic problems that can affect a typical heat exchanger, including fouling, tube leaks, and air and vapor binding. We also looked at the causes and effects of these problems, and we saw how they can be dealt with. Let's take a moment now and try some practice questions. Fouling can sometimes be minimized by adding chemicals to the fluids passing through a heat exchanger. For example, chemicals such as chlorine are often added to cooling water to reduce the amount of algae or other organisms inside a unit. Corrosion chemically deteriorates tube metal to create a leak. Corrosion is caused by a chemical reaction between the metal in the heat exchanger and either the fluid passing through the unit or impurities in the fluid. The corrosion weakens the metal until a leak forms. Regardless of how gases get into the heat exchanger, the unit must be vented to allow them to escape. Repeated venting may be necessary to ensure that the heat exchanger remains free of air and other undesirable gases. However, excessive venting can cause its own problems. For example, each venting may allow a small amount of the process fluid to be lost from the process. This reduces the efficiency of the process.